Hello everyone. Today inshallah we will continue on the previous sheet. I want to go with you with some problems. I will try to finish this sheet today, and for the second lecture we will go to cover the slides, the 7th and the 8th lectures inshallah. I would like to start with you with this formative exercise. We plan to have it today. This is very, very simple. The first one is asking you to determine or to identify the domain of rho t, where rho of t is equal to 1 over t in I plus 1 over root 2 minus 1j plus 1 over t minus 2 in the k direction. Also, I want you to compute rho dash and rho double dash. This is a straightforward derivative. There is no ideas in it, but I want you just to try it by yourself. Also, for the problem number 10, it's given rho 1 and rho 2, and he asking you to find the following derivatives. It's really very simple. All you have to do is to just go through the process of derivative. If I want to solve the first problem, it's really very easy. In order to determine the domain of rho t, which is simply, as you can see, rho of t consists in the direction of I plus direction of j plus the component in k. All the components must be satisfied and the conditions has to be well taken care of. So the first component is simply 1 over t. The second component, as you can see, it's just simply 1 over the root of t minus 1, okay? And the third one is 1 over t minus 2. So if I want to get the domain for rho of t, I must be sure that all the components are satisfied and easy to work with. So the first condition is that t shouldn't equal to 0 in order to satisfy the I component. For the j component, I have a square root in the denominator, which implies that t minus 1, this is the second condition, t minus 1 must be greater than 0, which leads to t must be greater than 1. So this is the first condition, and that's the second condition. Remark that the second condition, we are talking about an interval starting from 1 up to infinity, which means we are already excluded the first condition, so both of them are satisfied with this condition for the second component. If you look to the third one, okay, to the third component, the third component states that t minus 2 shouldn't equal to 0, which means t shouldn't equal to 2. That's the third component. So if we are dealing with the real number, this is the real number, the x-axis, this is positive infinity and that's negative infinity, as you know. Here's the 0 is an open one, and for our domain, we will start from 1 open and to go up to infinity, but we will try to exclude the value of t equal to 2. So this is gonna be an open circle like this, or an open point. So if I want to try the domain, so simply the domain of rho t is gonna be t belongs to the open interval, which starts from 1 up to infinity, except the value of 2. Or you can write it like this. The t belongs to the interval which is open at 1 and also open at 2, union, starting from 2 up to infinity. It's really up to you how to put or describe your domain. So this is going to be the domain. It's really very simple, as you can see. Okay, we want you to get rho dash of t which is simple, which means that you will need to differentiate each of these components. So simply all I have to do while we are getting rho dash of t, it's gonna be differentiating the first component, and I think that the best form to start this derivative is to consider that rho of t, let me write it here, rho of t is gonna equal to, just in seconds, sorry, okay, we can write rho of t equal to t to the power of -1 in the I direction plus t minus 1 to the power of -1/2 in the jth direction plus a t of -2 to the power of -1 in the case direction. Then getting rho dash is going to be a very easy task for you to do, or even rho double dash if you want to get the acceleration of this function. It's going to be easy. So differentiating the first one is going to be a negative of a t to the power of -2 in the I direction. Differentiating the second one is going to be -1/2 times t minus 1 to the power of -3/2 in the j's direction. For the last component, it's going to be a negative of a t minus 2 to the power of -2 in the case direction. Also, I can leave them like this or rewrite them as 1 squared in the ith direction. The other, or the second component is going to be -1/2, and this is going to be a square root for t minus 1 to the power of 3 in the j direction. And the last component is going to be 1 divided by t minus 2 to the power of 2 in the case direction. These are the derivatives, as I told you, for rho dash. If you want to get the second derivative, all I have to do is to differentiate once this component. So it's really very simple to see this. This is the first requirement, which was the domain, and it's exactly as I told you. You can write it this way, or you can write it that way. And for the first derivative, this is what we are going to have. For the second derivative, also once more, I would like to have this form, which is going to be simpler for me to get the second derivative for. It's going to be a straightforward process. So the first one is going to be 2t to the power of -3 in the direction of I, and the second one is going to be -3/2 minus 1/2, so it's going to come up to 3/4 as you can see. So it's just simply plus 3/4 times t minus 1 to the power of -5/2 in the direction of j, and for this the third component, it's going to be a plus for a 2 times t minus 2 to the power of -3 in the direction of k. It's very, very simple, straightforward. Everything is really very nice and gathered together nicely, as you can see. For number 10, question number 10, you have in rho 1 and you have in rho 2. And he is asking you to find the derivative of rho 1 dot rho 2. This is a multiplication, so it's really very simple. All you have to do is to get the derivative of rho 1 times rho 2, then plus rho 1 times the derivative of rho 2, and you are all set and you are done. Of course, if you need to make some simplifications, it's okay. I will leave this as an open exercise for you. Please try to do your best just to make the results gathered to cosine 2t in j minus 12t to the power of 5 in k. I will leave this with you for the next lecture, inshallah. And for the rho 1 t squared, all you have to do is just to replace these amounts. Instead of t, you will have t squared, so it's going to be t squared. This is going to be t squared, this is going to be t squared minus 2. Then, this is for rho 1, so this function. All I have to do is to change t to t squared. This is going to be sine t squared. This is going to be t Yes, exactly right. So it's going to be t to the power of 6. And then to start differentiating, it's a very simple process, but just try to go through it on your own. If you have any problems, we can go through it next lecture, inshallah. Okay, I will go forward for the next question, and it's a really very nice question to go through. Just give me a second to read this. Okay, very good. For problem number 11, he's telling you, let rho be a differentiable vector function in R, such that, there's the condition. Rho dash of t doesn't equal to 0, that's for every t. Show that if t naught is a local maximum point. So we need to check what's the condition to have a local maximum point of the function tau of t, which is simply the magnitude of rho of t. Then get rho dash and then rho dash and rho t are perpendicular on each other. Let me go through this with you. He wants you to show that if I have t naught as a local maximum point, okay, and tau is the function, as you can see, which is the magnitude of rho of t, then try to prove that rho dash at t naught and rho at t naught, both of them are perpendicular. Okay, how to proceed? In problems like this, you will have to find, first of all, you will have to think, read it more than once, and then start with just putting your ideas on the board, step by step. So let me see where to start. Okay, I will start from the definition of the function that's given by tau of t. So he's telling me that tau of t is simply the magnitude of r of t or rho of t, which is given. So it is the magnitude of rho of t. Now let's think what we mean about the magnitude of a rho of t. What we mean about this magnitude. It's really very simple. To find this, so tau of t, or the tau function of t, is going to equal to a square root which contains rho of t, okay, to the power of 2, which means rho of t times rho of t. If you come to this fact, and this is the main function that we need to find a maximum point for it, then the problem will be solved easily. Now come to the point, or to the what we mean about a maximum point, or what's the condition to have a critical point through a function. To have a critical point, we will need to find the first derivative and both the first derivative equal to 0. So at any critical point, the first derivative at the critical points will equal to 0, and this is the main point that I will depend on it in proving what he needs me to do. So the first thing that I will do, I will try to get tau dash of t. So let's differentiate this function. We have a square root, where we have rho t times rho of t. So start differentiating. I will differentiate the square root first, which is going to be 1 over 2 of the root of rho t dot rho of t, which means I have rho of t to the power of 2. This is the function inside this bracket. In order to differentiate a function to a power, I will have to differentiate the power first. So this is going to be the derivative of rho of t. It's going to be, let the 2 to go down and take 1 from this power, so it's going to be 2 rho of t, then times the derivative of this function. It's really forward and very simple. So once again, I've started the idea to start with, or to see how to prove this statement. I've started from tau of t equal the magnitude of rho of t. I started from this point. So the magnitude is going to be, it's simply the square root of the square of the components, various components of this function, which means rho t times rho t. Since rho t is a parametric function, so it has components in I, j, and k, and since I, when you multiply them together, you will have just only the components to the power of 2, that's I squared, j squared, and k squared, and so this is why you will have rho t to the power of 2. Now start differentiating. I will start differentiating with the square root, which is going to be 1 over 2, the root of rho t times rho t. In a similar manner, same way like, I will go through differentiating rho t to the power of 2, which is the function inside this bracket, which is going to be, the 2 will go down, and then subtracting 1 from this power, so it's going to be rho of t, times the derivative of rho of t, which is going to be rho dash. Now to simplify things a little bit, so I will take 2 from the numerator with 2 from the denominator. This will come again once more to be the magnitude of tau, so it's going to be the magnitude of rho function of t, and for the denominator I will have the following. I will have rho of t times rho dash of t, and that's the definition of tau dash of t, the first derivative of my function. Okay, once more, he wants me to show that if t naught is the local maximum, which means at this point, the first derivative must equal to 0. That's will lead to tau dash at t node must equal to 0. If you look at this function at t node, and that's the given information, which means that rho at t node times rho dash at t node divided by the magnitude of this vector function rho of t node, okay, this is gonna equal to 0. To have this quantity equal to 0, then the denominator must equal to 0. Now I came to the point that states that rho of t node dot rho dash of t node equal to 0, which is the condition that rho of t and its derivative are perpendicular on each other, and the problem is proved. This is very simple question. The main idea is not how to solve this problem in particular, but the main thing is to how to think, how to start the first step. As I told you, I did go through the statement once more. It's rho be a differentiable function in R, and rho dash doesn't equal to 0 to avoid that the derivative by itself is equal to 0, and that's for every t. Show that a t node is a local maximum point if the function tau of t equal the magnitude of rho of t. Okay, then rho dash at t node and rho at t node are both of them are perpendicular. As I told you, I will start once more with the main function, which is tau of t. Now the magnitude or the norm of the vector function rho of t is going to be given by the square root of rho of t dot rho of t. These two functions will be a dot product in each other, so this is the magnitude of this function. Okay, I will need the condition for maximizing is to find the first derivative, and the first derivative must equal to 0. So rho dash is going to equal to the differentiation of this square root, which is going to be 1 over 2 the root of root rt times rt, times the derivative of the function inside this bracket, which is going to be at 2 r of t times r dash t. Now we came to the point that I have the first derivative. Try to simplify it a little bit. You will remark that the value on on the denominator, this value on the denominator is exactly the magnitude of this function. So I will eliminate 2 with 2, and then, okay, as I told you, this is going to be the magnitude of r of t, and then I will have the denominator rho times rho dash, or r times r dash again. These two functions, or these two components for the denominator, to have a maximum point at t naught, all I have to do is to replace these two guys by t naught. So I'm trying to make the substitution for 2 of t at t naught. Once you do this, you will end up having this value. The denominator will never equal to 0, because if it is equal to 0, it means you will have an undefined quantity. So all I have now is to have that r t naught times r dash t naught equal to 0, or rho times rho dash equal to 0, which is simply the condition for these two functions to be perpendicular on each other, as we saw. This is very, very nice problem. I would like you to solve it once more using your paper and pen, rewrite it again, and try to prove it in a similar manner. Okay, for the problem number 12, he's giving you that this information. Let me clear this first. He's giving you that suppose that we have a particle, and this problem is very nice also. This is a very nice problem that will be solved very easily. He's telling you, suppose that I have a particle follows a bus of C described by, so now you have r of t, or the description of this function, r of t here, okay, this is r of t, which is simply, it's gonna be e to the power of t, okay, in the I, and for the j component, it's simply e to the power of negative t in the jth component, and for the kth component, it's cosine t, so it's simply plus a cosine t in the case component. So this is r of t defined in the I, j, and the kth components. And he's stating that until time t0. So once more, suppose we have a particle follows a bus of C described by this function until, or this curve, until t equal to 0. After which it will follow the tangent line at C. So I will need to get the equation of the tangent line at C. Okay, of this curve. At this instant where the particle located at t equal to. So mainly I will need to get the equation of this tangent. In order to get the equation of this tangent, I will have to get r dash t. And this is going to be very, very simple. All I have to do once more is to differentiate all of these components. So it's going to come up to e to the power of t in the i's direction, plus start differentiating the second component, which is going to be a negative, of an e to the power of negative t in the j's component. And the last one is going to be a negative of a sine of a t in the case component. These are the derivative of r of t with respect to t for the three components, as we can see. And if I want to locate the exact position of this vector at t equal to 0, all I have to do is to start substituting in this in the main function by t equal to 0. So r at 0 is going to be simply e to the power of 0, e to the power of negative 0, and cosine 0. And this is going to come up to the point where this particle at the time being, which is going to be 1, and the cosine 0 also is equal to 1. So this is the main point. Now to the direction of the tangent, which at this point also, which means if I want to have r dash at 0, which is the direction and at time equal to 0, all we have to do is to start substituting this function exactly the same like we did before, but in this case we will get the vector of this tangent time. So start substituting is going to be e to the power of 0, which is going to be 1, e to the power of 0, which also going to be 1 times negative, so it's going to be negative 1, then minus sine of a 0, which is going to be 0. Now I have the direction of this tangent line, and I have a point on this tangent line. And as you know, the parametric representation of the tangent line, so if this is the tangent line, and the parametric representation is going to be at the point plus lambda, where lambda belongs to r, times the position vector of this tangent, which is going to be r dash at the point that you working with. So simply the equation of the tangent at t equal to 0 is going to be the first point, which is triple 1 plus a lambda times r dash, which is going to be a 1, negative 1, and 0. This is mainly the equation of the tangent line. And he wants you to determine the position of this line, of this particle after t equal to 2. Now, once more, he told you that suppose the particle follows a path, which is c, until time t0, so it's following until t0, after which it will follow the tangent. Here is the equation of the tangent. All I have to do is to start substituting by the parametric value, which is equal to 2. So all I have to do now is replace this guy by t equal to 2. And now I will have the exact position of this particle. So it's going to be 1, 1 and 1, and it's going to be plus 2 times 1, negative 1 and 0. So it's going to be 1 plus 2, so it's going to come up to 3. 1 plus negative 2, which is going to be negative 1, and 1 plus 2 times 0, so it's going to be a 1, and this is exactly the position at the tangent line. Once more, all the steps, as I told you, it's really very simple. So computing the position at t equal to 0 is going to be simple. All I have to do is to start substituting in this function with t equal to 0. So that's the x component, the y component, the z component, or the component, the i's, the j's, and the k's components. So this is the point that we interested in at the position at t equal to 0. The velocity tangent, or the vector, is going to be given by just differentiating what's given, the main function. So it's going to come up to et, differentiating a minus t once more. It's going to be a negative e to the power of negative t. Then cosine t, once you start differentiating, is going to be negative sine of a t. Start substituting by t equal to 0 to find the direction of this vector, which is going to be 1, negative 1, and 0. Now I can write the equation, the line equation, the tangent equation, point plus lambda direction vector. Done. Then you need to determine the position. All I have to do is just substituting by lambda equal to 2, and you will have exactly the same result, which is 3, negative 1, and positive 1. This is also a very nice problem. Please, I want you to go through these problems once more for the 1000th time. It will never make any sense just watching without using your hand. I've sent you the PDFs for this lecture, and I believe I sent you also the PDF. Let me check. I will be sure to send you the main PDF of list number 4, just to be with you and try to solve it by your hand as I recommended and as I told you. The last problem in this test is problem number 13, which is very, very important problem. It's covering most of the ideas that we did go through this this part in our course. The part of the parametrization, the arc lengths, how to parameterize the curve using the arc lengths function, and so on. This is really a very important problem, and I would deeply recommend that you solve it once more as a equation. Here, he's giving you, consider the vector function, he's giving you a vector function, which is given by t over t by 2 in the ith direction, cosine root t, root 2 times t in j's direction, and sine root 2 times t in the k's direction. Remark that t belongs to the interval, or starting from 0 and covering up to 2 pi. And let C be the parametric curve divided by rho. So this is the curve, which is C. Suppose that C represents the trajectory of a particle. And we did go through this previously, because once you have a function in parametric form, all you have is just the trace of this points, okay? And once you start putting t equal to 0, you will have the position at t equal to 0. At t equal to 1, you will have the position at t equal to 1, and so on. So starting from 0 up to 2 pi, you will have that trace moving around and giving you the curve. Okay, look to the amount. Just look at this. You have what we have. You have A, B, C. This is 1, 2, 3, 4, 5, 6, and 7. 7 requirements that can be you can be asking about them for this problem. The first question is to find the unit tangent vector at each point on the curve. I need to find the tangent or the unit tangent vector at each point through this curve. How to find this? This is really very simple. All I have to do is to regain once more. This is the vector function that we are dealing with, which is t over 2 cosine root 2 of t sine root 2 of t. Then I will start by getting the equation of the tangent line, which is really very simple. The unit tangent vector, it's r dash of t divided by the magnitude, which is really very simple. All I have to do for the once more, I will try to get r dash of t, which is very simple. I will have 1 over root 2, and please be careful about this in the derivative of each component to avoid any mistakes in any unnecessary mistakes. Cosine root 2 of t, once you start differentiating, it's going to be a negative of a sine root t of 2 times root 2. And for the last component, I will start differentiating sine root 2 of t, which is going to be a root 2 times cosine root 2 of t, and this is r dash. So now I got r dash. I will need to find the magnitude in order to find the tangent as a unit vector. So in order to get the magnitude, it's going to be simple. All I have to do in order to get the magnitude of r dash is to get the square, the sum of the squares, the square root of the sum of squares of these components. So it's going to be simply 1 over 4, then plus, I will get this quantity to the power of 2, which means I will have 2 times sine square of a root 2 in t angle, plus the last component, same way like, I will square it, so it's going to be a 2 times cosine square of a root t in 2, all of this under the square root. If you remark, this is our famous law about the trigonometric functions, which is going to come up to 1 over 4 plus 2, just only 2. And getting the sum of these numbers is going to be the square root of 1 over 4 plus 8 over 4, as you know, which is going to be the square root of 9 over 4. That's going to come up to 3 over 2, and that's the value of the magnitude of the r dash. Now to get the tangent, so the tangent at t is going to be simply r dash at t divided by its magnitude. So all I have to do is to get these components divided by 3 over 2, so it's like multiplying all of them by 2 over 3. So it's going to come up to 2 over 3, and then 2 over 3 times this guy, so it's going to be negative 2 root 2 over 3 to the sine of root 2t, and in a similar manner, so it's going to come up to 2 root 2 over 3 times a cosine over root 2 of t, and that's mainly the tangent equation that we need to find. So once more, as I told you, this is rho dash or r dash, which is simply the differentiation or the derivative of this function. Each component of these vectors really differentiated. The second step is to find the magnitude. So each one of them is squared, as you can see. The last step is to divide. So of course, we simplify in order to get 3 over 2. Then I will get the unit tangent, which is r dash over the magnitude of r of t. So all I have to do is just to divide the row vector function or the vector function for the derivative by its magnitude. So it's going to come up to this guy times 1 over 3 over 2. Of course, the denominator is a denominator. This is why I will multiply by 2 over 3, and this is the final result. As you can see, it's exactly the same way like. See, simple, but still it needs you to focus on all of this. For the second requirement, he will ask you to compute the length of the curve. If he wants you to evaluate the length of a curve, it means the arc length. Okay, how to get the arc length? I would usually prefer to get the arc length function, then start substituting in the arc length function. So simply, if you want to have the arc length function, start to remember, it's simply an integration from 0 up to t for r dash, and the r dash is given r dash, the magnitude, of r dash of t. So this is r dash of t with respect to dt. So this is mainly what we are going to have. This is the law that we will use. Okay, simple. Okay, I will take the magnitude of r dash of t